the gauge symmetry can be made both continuous and discrete. Why? In some theory, so-called lattice gauge model, you can discretize. So you can discretize space-time, you discretize many, and this is not due to the fact that space and time are discrete, but because this discrete model can represent the true experimental result. Why? For the moment, don't ask me. Because you know, in mathematics there is always two equations. One called differential equation. The other is called difference equation. They are the same thing, but one in discrete form, the other in continuous form. So this is the nature of mathematics. You can have a continuous variable, or you have a discrete variable, and the continuous can also be discretized. So that's so it's just a tool, and the symmetry can be made also into this form. But for this introduction, I will specifically stress on the continuous part. The discrete part is shown only for certain. Later we will see the charge conjugation is also another discrete operator whereby it changes everything, every quantum number to the opposite, from particle to its antiparticle. So a charge become, if it is plus, it become minus, and spin, if it is up, it become down, and so on. So those are the what you call it, and momentum, positive, negative, and so on. So those are for charge conjugation, and without changing, for example, the value of the spin or the kinetic moment. So let me just show you what you mean by gauge symmetry. So actually, the first idea of gauge symmetry comes from electromagnetic interaction. And this is actually the first what you call it, force that is successfully formulated. Okay? Why? Because it involves electricity, it involves magnet. And this phenomena, you can do the experiment even in the school. You can see magnetic force. If you have a magnetic pole piece which is north-south, and you throw the iron filing, and you can see the distribution of the magnetic field. So this, and but however, the first successful experiment theory was by Maxwell. So that's how you get the Maxwell equation, the so-called classical electrodynamic. And why classical electrodynamics, even today, so-called electromagnetic theories difficult? Why? Because it involves tensor. So that's why it's difficult. Or sometimes called Maxwell theory. And how does it come about? Very simple. In this Maxwell theory, it assumes two variables. The first one, two main variables. That is A, the so-called vector potential, and B, no, not B, V, which is a scalar potential. In fact, you can go beyond the EM interaction to formulate what you call 5 dimensional, because this involves typically 3 dimension, you can go to 4 or 5 dimension. You can add tensor potential. So this is what people try to do to generalize EM interaction to higher dimension. So it's obvious that you start from scalar, you go to vector, and then the next you go to tensor potential. And tensor have rank, so the higher rank will give you to higher dimension. So this is in fact, vector is a rank 1 tensor. So this is this is already successful to explain the phenomena. So how, for example, in this theory, the magnetic field is given as the curl of A. So this is magnetic field. So what's strange about this definition of magnetic field, which is the curl of A, curl of the vector potential? If you add to this B, if you add to this vector potential an arbitrary value, say to A is added this some gradient of some field alpha. Obviously, alpha is scalar. Okay? But when you take a gradient to a scalar, it becomes a vector. But you all know that the curl of a grad is 0. So this mean that this is cause this thing to not changing. Okay? Because the curl of a grad is 0. So the physics is the same, even though A has changed from A to A plus some gradient. So this is having you this give an idea that so B unchanged, meaning that you can have the same physics, the same phenomena, even though A has shifted from A to A plus grad alpha. And similarly, the electric field is defined by minus grad of V, the so-called scalar potential, minus rate of change of the vector potential. In fact, if you take the curl of E, you take the curl of this E, you will get a minus d by dt of the magnetic field, the rate of change, and this is called the Faraday-Lens law. Since the rate of change of the magnetic field give the curl of E. Now, what happens if you change? So let V change to V minus E alpha by dt, where, as I said, alpha is a arbitrary scalar value or function or field, whatever you call it. And similarly, A change from A to A plus grad alpha. You will see that if you plug these two values here, V here, in here, you replace, and this value you replace here, you still get the upper curl of E unchanged. Sorry, you get E unchanged. Not the curl, the E itself doesn't change. So of course the curl also unchanged. If E doesn't change, the curl also doesn't change. So many different potential, which is this one and that one, yeah, does not change E and B, and describe, or other words, describe the same physics. So this is the idea of gauge invariant. Idea of what you call gauge invariant. Different potential giving the same physics. Now, let's look, because classical electrodynamics is classical, it's not quantum. Okay? And modern physics all require quantum phenomena. So let's look from the view of quantum physics, what this gauge invariant is all about. So let's look at quantum mechanically. We know that